Assalamualaikum warahmatullahi taala wabarakatuh. Today, Madam going to continue our lecture on chapter 7, topic magnetism, part 2. Whereby within this part 2, Madam going to discuss on subtopic 19.5, 19.7 up to 19.8. Let's begin. 19.5, magnetic force on a current carrying conductor. So previous lesson we've learned about how the magnetic field going to affect moving charge, right? Still remember the direction, the force, the B, the velocity, the angle, based on the formula F equivalent to QVB sin theta. So within this subtopic, okay, we are going to discuss on the force acting on a current conductor, current flowing within a conductor, where instead of only a charge moving, now we have bundle of charge moving within a straight long conductor. Okay, so the current is a collection of many charged particles in motion. If you still remember, definition of current is the rate of flow of charge. Right, so if you have bundle of charge flowing within a conductor, and of course, the bundle of the charge going to experience magnetic force whenever they are placed within an area, a situation where there is a B or magnetic field. So the direction still, we are going to use first right hand rule. So let's recall, the thumb is your force. Here, the direction of your thumb is the force direction. Your index finger, supposedly the direction of the V. Okay, the rest of the fingers will be the direction of your magnetic field. Right. So, refer to this figure. In figure A, we have a long straight conductor. Okay, long straight conductor, whereby the middle section of it is immersed in magnetic field area, whereby the B is into the page. Okay, represented by the cross symbol here. At this instant, the current is not flowing yet. Okay, the I is 0 in this moment, so there is no effect of force experienced by the long straight conductor. Okay, so now second figure, you have the current flowing upward. Okay, current flowing upward, and the B is into the page. By using right hand rule, everyone, you have to follow me, you have to try, okay, together with me. Now touch the screen. Okay, your B is into the page. Your velocity direction now is similar or same to the current direction. Instead of V, now your index finger going to be the direction of your current. Okay, so your current upward, so index finger is upward. Right, so if you see here, your thumb is pointing to the left, meaning that the force experienced by the straight conductor here, having current flow upward here, will be to the left. That is why the middle section here is skewed or pushed to the left. Right, so again, whenever there is current flow downward, right, downward direction, okay, the B is into the page. Then now, by using right hand rule, your current direction is pointing to down direction, to the bottom of the screen. So use your index finger to represent, to follow the direction of your current. Index finger, the direction of current is direction of index finger. Alright, downward. Then your B is into the page, so your thumb pointing to the right. That is why the wire now skewed to the right. Okay, the middle section especially. Alright, so let's recap again. instead of velocity, now we are going to use here, okay, I direction. Okay, this is on how to use right hand rule number 1. Right, then next one, the force itself, okay, instead of QVB sin theta, now we have a new formula because we have new adaptation of collection of bundle of charge, right? So it's BIL sin theta, right? So angle is between vectors, smallest angle between vectors. So between what vectors? Between the B and also the current flow. Okay, current flow. Of course, the current flow within the length, the same length, right? Okay, so the unit is Newton. The theta is smallest angle between B and I. Alright, the direction is found by the right hand rule, placing your fingers in the direction of I instead of, this is supposed to be velocity. Alright, so example 19.5, you may try out this one, okay, on your own. Right, now I don't want you to try. Let's go together, let's try together exercise. This is question number 32 at the back of your textbook, chapter 19. Right, so a horizontal power line of length 58 meter carries a current, okay, of 2.2 kilo ampere as shown in figure. Earth magnetic field at this location has magnitude equals to 5 times 10 to the power of negative 5 Tesla and makes an angle of 65 degree with the power line. Find the magnitude and direction of the magnetic force on the power line. Okay, so if we refer to this, okay, angle already given between the current flow and the B of the earth. The B of the earth is represented by the green color here. Okay, so the angle is 65. Now we're going to solve it. Okay, as we know, right, F is equivalent to BIL sin theta. Alright, so what is our B? 5 times 10 to the power of negative 5 times current. Current is, where is it given? 2.2 kilo. 2.2 times 10 to the power of 3 times the length of it, 58, times sin, what's the angle? 65, because the angle between the B and the current, okay, is already given 65. Okay, so 65 degree. So from here directly you will get the magnitude of the force is 5.8 Newton. How about the direction? The direction, everyone, all of you, please try together with me. Touch your screen. Right, so index finger is pointing to the direction of the current. Okay, the B is almost about downward, okay, but having a slightly 65 degree from I, and your thumb is pointing into the screen or into the page. Okay, so the direction of F is into the page, okay, or our screen lah. In this our case here. Okay, then next one will be magnetic field, long straight wire. Okay, so just now what we've learned about just now, we are learning about how external magnetic field give effects or cause force, okay, experienced by a long straight wire having current flow within it. Okay, this is vice versa of it. Okay, so this one is how a long straight conductor having current flow, okay, somehow produce its own magnetic field surrounding it. Okay, without considering the external, by itself, okay, the the long straight conductor that having current flow within it is actually producing its own magnetic field. So it's contradict to whatever we've learned just now. Right? We've learned just now there is external field. What will happen to the conductor having current flow within it? Okay, so this one, a long straight conductor having current flow within it, somehow we can detect B surrounding it. Okay, so we have here long straight conductor, alright, having current flow I to the top of the page, alright, and if we place a needle compass surrounding the conductor that having current flow in this instant, we somehow going to detect deflection of the needle compass in some method. Okay, so the direction of the needle compass, we representing the direction of the P, right, of the P. Okay, so how to determine the direction of the needle compass? Okay, by using right hand rule number 2. Right, so how to do it? Your thumb, place your thumb along the direction of the I. Your thumb is placed along I direction. Okay, grabs the conductor. Okay, please grab the conductor. Imagine you can grab the conductor. The direction of your fingers, okay, grabbing the conductor will be the direction of your P, right? So in this case, the direction of your B will be in this direction because according to your fingers direction when you grab the conductor. Right, this is right hand rule number 2, also known as grabs rule. Right. Okay, so magnitude of the field along the straight wire. Okay, the magnitude of the field at a distance from R from a wire carrying conductor of I is given by B equivalent to B equivalent to mu naught I divided by 2 pi R. Okay, mu naught I divided by 2 pi R. So mu naught is permeability of free space. The value is actually mu naught equivalent to 4 pi times 10 to the power of -7, right, Tesla dot meter per ampere. Okay, this is a constant. Alright, you also can figure out this from your calculator actually. Okay, so what does that mean by this equation? Okay, it means that, right, it means that the B is inversely proportional to the distance from the conductor. So if let's say you have a long straight conductors, right, along straight conductors, right, and then surrounding there is a current flow within the conductors. Okay, current is flowing in this direction. All right, so surrounding the conductors will be grabs rule, will be B in this direction, isn't it? All right, so B okay, the distance from this point to this point, right, the R, okay, will give a value of B variably. Okay, so means that the bigger the R, the smaller the B. Okay, because the more distant, the bigger the distance, the far away from the sources of the magnetic field, the strength of the magnetic field will be reducing. It's inversely proportional. Okay, so the value of B at this instant, let's say B1, compared to this distance, let's say B2, will be varied according to this. right? Next one will be Ampere's law. This is actually Ampere's law talking about how to produce the formula just now. What formula? B equivalent to mu naught I over 2 pi r. That formula. Okay, how to actually derive that formula. So Ampere's talking about, okay, a procedure found that, okay, deriving the relationship between the current in an arbitrarily shaped wire and the magnetic field produced by the wire. Ampere's circuital law saying that summation of, right? Summation of, this is actually summation of B parallel to the length, small chunk of length, is equivalent to mu naught I, okay, for a closed path. So from here, by using this approach, this one is actually pi, okay, right? Use a closed circular path is actually an approach, okay, to have instead of arbitrary shape. So now if we consider a circumference of a circle is good enough, B is equivalent now mu naught I over 2 pi r. This is actually the same thing to what we have before.